Let's go.
Basic principles of why and how airplanes fly apply to all planes, from the Wright brothers' first machine, Wright flight, to a modern stealth bomber. And those principles are the same for radio control and full-size airplanes alike. Although the true physics of flying airplanes are quite complex, the whole subject can be simplified a bit enough for us to get a fundamental understanding of what makes a plane fly at least. Aerodynamic forces. Essentially, there are four aerodynamic forces that act on an airplane in the flight. These are lift, drag, thrust, and weight. In simple terms, drag is the resistance of air molecules hitting the airplane, meaning is the backward force. Thrust is power of the airplane's engine, meaning is the forward force. Lift is the upward force, and weight is the downward force. So for airplanes to fly and stay airborne, the thrust must be greater than the drag, and the lift must be greater than the weight. So, as you can see, drag opposes thrust and lift opposes weight. This is certainly the case when an airplane takes off or climbs. However, when it is in straight and level flight, the opposition forces of lift and weight are balanced. During a descent, weight exceeds lift, and to slow an airplane, drag has to overcome thrust. In the picture, let's look at the forces affecting the aircraft. Thrust is generated by the airplane's engine. Weight is created by the natural force of gravity acting upon the airplane, and drags come from friction as the plane moves through air molecules. Drag is also a reaction to lift, and this lift must be generated by the airplane in flight. This is done by the wings of the airplane.
The back of the engine. This is basically done by the large fan at the front of the engine, through which air passes at a high rate. These are the various components of the CFM56-7B. The fan, which is a large diameter propeller. The low and high pressure compressors with 12 stages which, step by step, increase the pressure of the air as it flows through them. The combustion chamber, in which jet fuel is mixed with air and burned. The high and low pressure turbines, in which the pressure of the hot gas is reduced as they drive the compressors and fan. There are 5 turbine stages, 1 high pressure and 4 low pressure. And finally, the exhaust assembly. The CFM56-7B is a high bypass ratio engine. The primary flow passes through the combustor, while the secondary flow passes only through the fan. 80% of the engine airflow, accelerated by the fan, is directed into the bypass duct and provides 80% of the engine's thrust. The primary flow passes in succession through the compressors, the combustor, and the turbines, before being ejected rearwards through the exhaust assembly. The air is compressed in the low and high pressure compressors, and its temperature can reach 450 degrees Celsius, after which it enters the combustor, where fuel is injected and ignited. Burning the mixture of fuel and air brings the temperature up to 1700 degrees Celsius. Finally, the accumulated energy is extracted in the 5 turbine stages immediately after the combustion section. The pressure of the air drops as it passes through the turbines and makes them spin, and the turbines, whose shafts ride within one another concentrically, in turn drive the fan and the 2 compressors. The air is then expelled through the primary duct, joining the air from the fan stream. A turbofan is therefore a flow cycle engine. Air is compressed, then heated by burning fuel, after which it passes through the turbines which drive the compressors and the fan.
The generation of lift has been an agreed theory in the past, but certain principles have been known about and agreed on for a long time now. A cross-section of a typical airplane wing will show the top surface to be more curved than the bottom surface. The shape profile is called an airfoil or aerofoil, and this shape exists because it's long been proven that an airfoil generates significantly more lift than opposing drag. It's very efficient at generating lift. During flight, air naturally flows over and beneath the wing and is deflected upwards over the top surface and downwards beneath the lower surface. Any difference in deflection causes a difference in pressure, and because of the airfoil shape, the pressure of the deflected air is lower above the airfoil than below it. As a result, the wing is pushed upwards by the higher pressure beneath, or you can argue it's sucked upwards by the lower pressure above. One of the argued but commonly discounted theories of lift generation is related to Newton's third law of action and reaction, whereby the air being deflected downwards off the lower surface of the wing creates an opposite reaction, effectively pushing the wing upwards. This may well be the case, but it's the pressure difference between the both surfaces that is commonly agreed factor of lift generation. The faster a wing moves through the air, so the action are exaggerated and the more lift is generated. Conversely, a slower moving wing generally creates less lift. It's important to note, though, that different wing design generate lift more efficiently than other design at different speeds, depending on what the plane has been designed for. A direct reaction to lift is drag, and this too increases with your airspace. So airfoils need to be designed in a way that maximizes lift but minimizes drag in order to be as efficient as possible. Angle of attack and lift. Another crucial factor of lift generation is the angle of attack. This is the pitch, angle at which the wing sits in relation to relative airflow around it. As the angle of attack increases, so more lift is generated, but only up to a point until the smooth airflow over the wing starts to break down, and so the generation of lift cannot be sustained. This point is called the critical angle of attack. When the CAA is reached, the sudden loss of the lift results in the wing stalling, and the weight of the airplane cannot be supported any longer. When a stall occurs, a sudden loss of altitude is inevitable unless the pilot rectifies the situation immediately by decreasing the AOA and getting the wing to generate lift once again. Typically, a stall recovery means simultaneously pushing the nose of the plane down and increasing power to gain airspeed. The angle of attack should not be seen as a less important factor in lift generation than the airfoil shape of the wing. In fact, the AOA is the single most important factor. For example, a flat sanction wing can produce adequate amounts of lift all because of the angle of attack. The big difference is in the efficiency of the lift generation. Flat wing sanctions carry a large penalty in terms of much higher drag, compared to an airfoil sanction where drag is substantially less. Airplane control surfaces. For an airplane to fly in controlled manner, control surfaces are necessary. The four main surfaces are ailerons, elevators, rudder, and flaps. To understand how each works upon the airplane, imagine three lines. Let's look at the blue axis lines in the picture. One runs through the center of the fuselage from nose to tail. One runs from to side, lateral axis, and the other runs vertical axis. All three axes pass through the center of gravity, the airplane's crucial point of balance. Located on the trailing edge rear of the wing, the ailerons control the plane's roll about this longitudinal axis. Each aileron moves at the same time but in opposite directions. When the left aileron moves up, the right aileron moves down and vice versa. This movement causes a slight decrease in lift on the wingtip by the upward moving aileron, while the opposite wingtip experiences a slight increase in lift. Because of the subtle change in lift, the airplane is forced to roll in the appropriate direction. When the pilot moves the stick left, the left aileron will rise, and the airplane will roll left in response to change in the lift on each wing. The ailerons are controlled by left, right movement of the control stick or yoke. The elevators are located on the rear half of the tailplane or horizontal stabilizer. The job of the tailplane is to generate a downward force to counteract the natural noise diving tendency of the planes, which happens as a result of the natural forces that are generated about the plane's center of the gravity and center of the lift. As the elevators are deflected up or down, so the amount of downforce change, and this result in the airplane's nose pitching up or down. However, pitching the nose up doesn't necessarily mean the plane will climb. In fact, it's quite possible to flying level or even descend with a nose up attitude. Only when power is added and speed increased will the plane climb with up elevator. Elevators are the single most important control surface of a plane, and they affect the airplane's airspeed more than to need to climb or dive. The rudder makes up to the rear portion of the vertical stabilizer or fan and is controlled by two pedals at the pilot's feet. When the pilot pushes the left pedal, the rudder moves to the left, while pressing the right pedal deflects the rudder to the right. The rudder works in the same way as ailerons and the elevators, in that it changes the airflow over the fin. Essentially, you can think of a fin as vertical wing. The air flowing over the fin and rudder acts in exactly the same way as it does flowing over a wing and aileron, except the forces are horizontal and not vertical. Deflecting the rudder to the left increases the air pressure on the left side of the fin and rudder, and so to the whole back and of the plane is pushed across to the right, thus yawing the nose to the left. Flaps are located on the trailing edge of each wing, usually between the fuselage and the ailerons, and extended downward and often outward from the wing when put into use. The purpose of the flaps is to generate more lift as a slower airspeed, which enables the airplane to fly at greatly reduced speed with a lower risk of stalling. When extending further, flaps also generate more drag, which slows the airplane down much faster than just reducing throttle. Although the risk of stalling is always present, generally speaking an airplane has to be flying very slowly to stall when flaps are in use, for example 10 degrees deflection. Obviously, although stall speed and safe airspeed vary from airplane to airplane. So all these factors are why and how airplanes fly. Rudder controlled planes can of course be more simple. For example, just have a rudder and elevator control, perhaps just rudder and motor control. But the same fundamental principles always apply to all airplanes, regardless of size, shape and design.